Hello, my name is Dmitry and welcome to the DP Labs channel. Today we will continue the topic of our titanium camper. In this episode we'll be making the battery, telling you about which BMS we'll use and so on. In this episode you'll see it all. I hope everything works out for us.
We're starting the third episode with assembling the battery, so we've already made this kind of aluminum sealed case, and we've also put together the holders for the assembly. Our battery will be made up of lithium iron phosphate 18650 cells with a configuration of 26S46P. That's about 1,200 of these cells, each at 3.2 volts and 1.1 amp hours. At this point, we've already placed all the cells into the holders and started spot welding. Before that, we also checked the voltage of every single cell because our batteries are used, but they still have plenty of capacity and cycles left since they're lithium iron phosphate and have a very high cycle life. We've also started welding using this kind of nickel strip and a Chinese spot welder like this one. Overall, the machine is really good for supercapacitors, and if you set it up correctly, it welds very well, but if you overdo it, it can even start burning through the cells. So here's the strip tacked in several places, and this is how the process goes. Even though the welding is done very quickly, it's very high quality. If you try to tear off the strip, we tested this on other cells, the strip itself tears, but the weld with a piece of the strip remains attached to the cell.
Gentlemen, I wanted to tell you about spot welders. We tried a lot of different ones for a long time. Tested them out. Before this, we used welders like these. Total junk, because they can't weld anything thicker than 0.15 millimeters. These are transformer welders. We even tried using thicker wires to reduce losses, put in AWG 2 wires, but still they just can't weld 0.25 millimeters at all. We can give them away to anyone in need. Just write to me. I can send them to you, shipping at your expense. Now we're using these capacitor-based spot welders with ionistors, an excellent thing. There's a link in the description, check it out. It's pretty expensive, but it welds like a pro. We're not even using it at full power, and it easily welds 0.25 millimeters. I think it could handle 0.5 millimeters if needed. It's a really good device. We just welded one part of the battery, it didn't overheat, didn't explode. Of course it gets warm with that much welding, but at least it's comfortable to work with. So, I recommend it.
So we've finished welding the second part of the battery. We've also brought out the wires for balancing from the bottom part. They're going to a 26-pin connector. The voltage at the moment is 85 volts, which is actually quite safe. You can touch it with your hands, there's no shock at all. Now, we're going to solder the balancing wires from here, and here are our outputs. We'll solder several wires together and connect them to the thicker wires, which will serve as our power leads. Now we've connected the BMS and decided to run the batteries through several cycles to measure their capacity and in general to see how they perform. The results were quite disappointing. We thought this was a used lithium iron phosphate 18650 battery from a Liebherr crane. We expected these batteries to have very good specs, about 15 years of service life and 5,000 cycles. As I understand it, they were used in some kind of emergency system, so the number of cycles should not have been significantly depleted. What actually happened was that we checked the voltage of each battery here, but we didn't measure the capacity. After assembling the battery, we ended up with an interesting situation. First of all, the BMS doesn't fully balance the cells during charging, because its balancing current is only 30 milliamps. In principle, we installed the batteries randomly, so theoretically they should have been more or less balanced. But in reality, at the end of charging, we get a 3.5 volt imbalance between the cells. All the cells are connected correctly, everything is displayed properly. For example, some cells are as low as 3.2 volts, while others are at 3.6 volts. It's unclear why such an imbalance occurs. The most interesting thing is that during discharge and charge, somewhere in the middle of the capacity or at mid voltage, they are more or less balanced. Sometimes the imbalance was even less than 1/10 of a volt. But when they approach the extreme upper and lower values, huge imbalances appear. The BMS, with its 30 milliamp balancing current, simply can't compensate for this. In this mode, when the BMS disconnects the battery based on the highest or lowest cell, its capacity ends up being tiny, about 1 kilowatt hour, maybe 1.5 kilowatt hours, which is very little. We tried discharging it, ran it through about 3 charge-discharge cycles, and the values seem to improve a bit, but only slightly. Still, this strange situation keeps happening. If anyone has encountered this, let us know what the problem might be. We think the issue is with the batteries themselves. Even if you look at the upper and lower voltages, when the BMS disconnects, the capacity is still very low, so it's possible they've lost most of their capacity. But we've decided not to throw this battery away just yet. We'll run it a bit more. Maybe it'll balance itself out, or we'll try to balance it artificially. Then we'll switch to these batteries. These are submarine batteries, lithium-ion, 150 amp hours. The battery will be 21p. They still consist of parallel cells, so when fully charged we'll have 8.4 volts from 150 amp hours, which is already much more. We expect that with this our little car will be able to run for a very long time.
So gentlemen, after all this bad news about our not-so-great lithium iron phosphate batteries, I've decided that so they don't keep bothering me, if anyone needs them, you can come pick them up yourself. We have about, I don't know, 4,000 or 5,000 of them, but they only show a maximum of 400 milliamps. Maybe they'll be useful for some of your tests or DIY projects. Pickup is from the Demodetsky district in the Moscow region. Write to me, come get them, I'll just give them away. Also, I wanted to say a few words about chargers. Right now, in our projects, we're using these kinds of chargers. They're fully sealed, take 220 volts input, and are designed for specific batteries. For example, this one is for 26S lithium iron phosphate with a 94.4 volts output. It monitors the charging current and shuts off automatically. Basically, it's a convenient thing. You'll find the link in the description. But for our kibitka, we'll try to make our own 3-phase charger. We'll use Meanwell power supplies as the base, so they can at least output 100 volts, or however much we need, and then we'll set up current regulation. I want it to charge from 3-phase power, so it'll be quick. So what else can I say? I've been really disappointed with large BMS units in terms of their balancing capabilities. Maybe we'll try capacitor-based active balancers. They can handle up to 5 amps, whereas 30 milliamps is pretty mediocre. By the way, soon we'll check the quad pack to see how it's holding up after use, whether everything's okay. But for now, it's running, not exploding, and seems to be working fine. In general, I have to say I'm not a big fan of the circuit design and construction of Chinese BMS units. They have some odd ideas, like running everything through MOSFETs at high currents and voltages, which just doesn't work. I think it's simpler to have the BMS control a powerful contactor. That seems better to me, even if it's less practical in terms of size. By the way, we should be getting some contactors soon, rated for 2000 amps. We'll see how they perform.
And now we'll tell you why we wanted to use a lithium iron phosphate battery. This blue one here is lithium iron phosphate. Kolya, go ahead. Nothing happened. And now actually a lithium ion 18650 battery. So we've welded the battery case and lined it with this kind of foam so the batteries don't rub against each other and for insulation. As I mentioned before, we'll have 20 of these batteries here, each with 150 amp hours. We've tested them and they really do have that capacity. We'll also have this kind of aviation connector for the BMS, and the BMS itself will be housed separately in another case. It's rated for 400 amps, though I don't think we'll need currents that high. We'll connect the batteries with these stainless steel plates 3 millimeters thick. This is how they'll be connected. Some might say stainless steel has high resistance, but each plate here has 120 square millimeters of stainless steel, and the distance between contacts is just 25 millimeters. So the resistance of this section will be very low. We'll also use this 50 square millimeter wire for the battery leads, and the wires for the BMS are even thicker. So I think we'll be able to draw the claimed 300 amps from this battery. Now, let's get to assembling. Connecting the batteries, soldering the leads to the BMS connector or something like that.
Guys, right now we haven't just been working on the batteries, but we've also continued working on our kibitka. Look, we already have the spot for the body. A lot has been welded and fixed up, so I hope it'll be ready to go soon. Also, for those special people who don't understand how a pendulum works, those who keep saying something will always hang, everything will tear and bend, we're going to show you that the suspension works just fine in this setup. Right now, not even Nikolai, who's a good weight, is going to sit here, but I'll try to rock it myself. As you can see, the suspension has some play, so everything's fine, nothing is tearing or breaking, and, well, it works just as it should.